The following program is brought to you by Caltech.
Good evening, and welcome to tonight's Watson Lecture. My name is Ken Farley. I'm the chairman of the Division of Geological and Planetary Sciences here at Caltech. And it's my pleasure to introduce tonight's speaker, Professor Brian Wernicke. Brian is a geologist, and his main interest is in the large-scale evolution of the continents. And he's interested in processes that are occurring on the continents on timescales that range from seconds to minutes to hours, so the earthquake timescale, all the way out to the geologic timescale over which mountain ranges are built. Brian uses classic geologic methods, including field geology, spends a lot of time in the field looking at rocks, trying to read directly what the rock record says, for example, by making field maps. And he also has a remarkable talent of bringing together new kinds of observations and techniques from other fields like geochemistry and geophysics to apply them in new ways to the problems that he is interested in. I'll say something about a personal observation I have about Brian. Brian is very much an iconoclast. It does not bother him that he has views that are quite different in interpretations of geologic phenomena. He's interested in important problems, and there are many ideas out there, and it doesn't bother him at all if his ideas are quite different than others hold, and I think you'll see some of this in tonight's talk. And one thing I'd say about being an iconoclast, it is usually not a very good way to be a scientist, because usually an iconoclast is reluctant to put forward a testable hypothesis that could falsify their iconoclastic view. This is not the way Brian works. Brian spends a lot of time working to develop a testable hypothesis, and then not only proposes a hypothesis, but pulls together the data or the team of investigators that are necessary to make the tests. He's been very successful working in this mode. Also, on a personal note, I've had the pleasure of working with Brian on several different projects over the years. I'm a geochemist, and I've worked with him on some of the problems, including the one we'll talk about tonight. This has been a remarkable pleasure for me. The way he approaches his science is very elegant, and I'll say I've never met somebody who could pull together so many seemingly unrelated facts about places and times in the past to bring to bear in his arguments. It's really remarkable how much information he has at his fingertips. So tonight he's going to talk about the origin of the Grand Canyon, which is really one of those classic questions in geology. It's been around forever. It's a stunning piece of landscape, and we still don't really understand how it was formed. And he'll give you an iconoclastic view. So in a moment, he'll speak, but before we get to that, I want to mention the Watson Lecture for next time, which is May 5th. The speaker is Chiara Dario, and Chiara is an assistant professor of aeronautics and applied physics here at Caltech. And she's going to give a talk called From Newton's Cradle to New Materials. That'll give you Brian Wernicke.
Well, thanks for that kind introduction, Ken. Well, before I start tonight, I kind of like to give, this is the third Watson lecture I've given over the last 17 years or so, and I like to share with you sort of a personal anecdote that I've shared with my students, I think, many times. And I got my PhD from a place called OIT, the Other Institute of Technology. It's in a state that will go unnamed, except that it rhymes with Taxachusetts. Anyway, the story revolves around Professor Norbert Wiener, who's a famous mid-20th century mathematician. And it gives an idea of what life is like around Caltech and what sort of people we truly are. So Wiener comes walking down this huge corridor at OIT called the Infinite Corridor one day. And he stops and is greeted by a couple of graduate students, and they have an animated discussion about the topic in his mind at the time. And when the conversation is over, he asks the students, "Which way did I come from? Which direction was I walking?" And the students were nonplussed, and they said, "Well, you came from over there." And he said, "Excellent, I've had lunch." Well, chances are pretty good that if you came tonight, you'd know that the T in T-Rex stands for Tyrannosaurus, and that the dinosaurs all died 65 million years ago when after a huge meteorite impact. The impact ended the Mesozoic era of Earth history and began the current one, the Cenozoic era. Chances are also pretty good that you visited Grand Canyon National Park, stood on the canyon rim, and wondered, how in blazes did all this happen? Speaking for myself, as of 2005, I knew a bit about both Grand Canyon and T-Rex, but never thought I'd be able to put the two together in the title of a lecture, at least in one that made any sort of scientific sense. Well, for one thing, the walls of Grand Canyon are made primarily of sedimentary rock, deposited during the Paleozoic era, between about 540 and 250 million years ago, too old to contain the remains of Mesozoic dinosaurs. For another, the 5 million people who visit Grand Canyon each year are told that it formed over the last 6 million years, carved by the erosive force of the mighty Colorado River. So as far as I was concerned, T-Rex just wasn't anywhere in the picture. But for me, at least, things began to change about 5 years ago when Ken Farley and I persuaded Rebecca Flowers, a talented young postdoctoral fellow, now on the faculty at the University of Colorado, to pursue a project to investigate when the canyon formed, which we'll get to in a bit. Now, the one place you do see T-Rex associated with Grand Canyon is along the railroad that circles Disneyland, which gets about 15 million visitors a year. I won't show any pictures of the famous dioramas here. I'll bet there's a dozen or so of you out there who haven't seen them yet, and I sure don't want to be the spoiler. But as the rest of you remember, just before you pull into the Main Street station, you go through a long tunnel where there's this big diorama of Grand Canyon. You see the lightning and a big thunderstorm raining down on all the stuffed denizens of the desert. Then the storm clears and the diorama ends. Seconds later, an even more impressive display comes along of the primeval world, complete with robotic dinosaurs. At the end of this spectacle, there's T-Rex and a Stegosaurus about to mix it up right there on the bank of a river of lava. Now, as far back as the 60s, I said to myself, why not include Grand Canyon in the backdrop for the dinosaurs? Instead of showing some big flat savanna like the one there in the poster. It seemed to me including Grand Canyon would make for one hell of a primeval world, boosting park visitation. You know, imagine a herd of spooked ultrasaurs plunging to their deaths. But I learned later there is a subtle scientific message behind the change in scenery from desert canyon to steamy plains, namely that Grand Canyon didn't exist when the dinosaurs were still alive. Not even the Disney Imagineers were willing to buck the science for dramatic effect. Dinosaurs old, canyon young is where Disney stands even today. And the bottom line is, so does mainstream science. But this was not always the case. Any talk about the origin of Grand Canyon has got to begin with Civil War veteran John Wesley Powell. He lost his right arm at Shiloh in 1862. A professor of geology at Illinois Wesleyan after the war, he was insatiably curious about geology and ambitious enough, among other huge accomplishments, to help found and eventually lead the U.S. Geological Survey. He became a national hero in 1869 by leading the first expedition to travel by boat across the little explored, bone-dry American Southwest, from southwestern Wyoming to southern Nevada, along the courses of the Green and Colorado rivers, including a traverse of Grand Canyon. Being the first to do this was only possible by anticipating the arrival of the Transcontinental Railroad at Green River, Wyoming in 1868. This made it possible for the first time to transport the expeditionary gear necessary to navigate the rivers that, remarkably enough, connect Rocky Mountain headwaters in Wyoming and Colorado with the Gulf of California. So if anyone in his era got it, that luck is where preparation meets opportunity, it was Powell. The first expedition began in May 1869 in Green River and ended in Colville, Nevada, 3 months later. Near the outset, they went through a 30-mile stretch of intermittent rapids in Lador Canyon on the Upper Green, where they immediately lost a boat and most of their supplies. Near the end, they faced nearly 300 miles of intermittent rapids in Grand Canyon. Now, doing this sort of thing in a large flat rubber raft with an experienced guide and helicopter rescue teams at the ready is one thing. Doing it in brittle wooden boats during a high water year, having no idea whether the next rapid would shatter more boats and strand the expedition in the middle of the desert, is quite another. Well, 3 of Powell's men didn't survive the stretch through Grand Canyon, though not like you might think. With just 2 days and 2 rapids left to go, they'd had it with the rapids. In modern vernacular, toned down from R to G, they told Powell that they were sick and tired of those mother-loving rapids on that mother-loving river. So they separated from the main party on foot by climbing out of western Grand Canyon onto the plateau to the north. Having plenty of preparation, but fresh out of opportunity, they were promptly murdered by Paiute Indians on the canyon rim, while the rest of the team floated safely on to Colville. According to accounts from the Shivwits Indians to Powell a year later, the unfortunates were mistaken for miners who had killed a Hualapai woman south of the river. Well, on to the science. Perhaps more than any single thing, Powell was fascinated by the fact that the rivers alternately flowed across expansive low-relief plains and narrow, deep gorges. So let's track it from north to south. Not far below the plains of Green River, the river runs eastward across a low-relief plain just north of the Uinta Mountains, called Brown's Park, of Butch Cassidy fame, then turns southward through Lador Canyon, which has very steep sides, more than 2,000 feet high. About 30 miles to the south, the river exits the gorge and flows lazily across the plains of the Uinta Basin. And then still farther south, the canyon walls begin rising again, and the river bisects the Tavaputs Plateau through a narrow gorge as much as 4,000 feet deep, eventually spilling out onto yet another low-relief plain. Below the confluence with the Colorado River, down in southern Utah, the river flows through its most dramatic gorge in northern Arizona, where the walls of Grand Canyon rise 5,000 to 6,000 feet above the river for an astonishing reach of nearly 300 miles. Below Grand Canyon, the river enters the Basin and Range province with its numerous mountain ranges and intervening basins, eventually working its way down to the Gulf of California, here and there cutting through gorges only a few hundred feet deep. Through the Rockies and Colorado Plateau, the alternation between flat plains and deep gorges struck Powell as highly counterintuitive, because river canyons typically originate in high-relief mountainous regions, with canyon relief steadily decreasing downstream. To explain the alternation, he came up with 2 basic concepts of landscape evolution, and in the process invented the scientific discipline now known as geomorphology. Now, for the first concept, if we make mountains by deforming the landscape, given that water must run downhill under the force of gravity, the streams will flow from high areas to low, as is evident here on the crests of these actively buckling mountain ranges in southern Iran. Here, the course of streams is a consequence of the deformation, and so we name streams like these consequent streams. For this hypothesis, a stream cannot cut across the uplift, contrary to what Powell observed on his expedition. So what's up with the Colorado and the Green? For the second concept, he saw an initial condition where a major stream, prior to the buckling, is already present on a low-relief surface. Buckling of the land surface so commences, and despite a tendency to form consequent streams, the erosive power of the pre-existing stream is sufficient to overcome uplift, and so it maintains its previous elevation and position. Powell called this type of stream antecedent. One of the best small-scale examples of this type is at Split Mountain, Utah, on the south flank of the Uinta Mountains. Here, rock strata are folded upward into an arch. On either side of the mountain, the Green River meanders on a low-relief plain, but cuts right across the arch as though it wasn't there, splitting it in two, as the name suggests. Powell viewed Grand Canyon as a larger-scale version of this phenomenon. Powell also proposed a more complicated variation of the antecedent stream hypothesis, where mountains made of hard rock are deformed and eroded, then buried by soft sediments that postdate the deformation, returning the landscape to a flat plain. Then a river formed on top of the plain can erode downward, removing the softer overburden, cutting randomly across the folding of the resistant, already deformed substrate. Powell referred to this type of stream as superposed. Seeing no clear-cut evidence for the third possibility, Powell came down solidly in favor of the antecedent stream hypothesis for the origin of Grand Canyon. Writing, through the entire region, I love this 19th century prose, though the entire region has been folded and faulted on a grand scale, these displacements have never determined the course of the streams. All the facts lead to the inevitable conclusion. Try writing inevitable conclusion in a scientific paper and see where you get. That the system of drainage was determined antecedent to the faulting and folding and erosion, which are observed, and antecedent also to the eruptive beds and cones. You certainly wouldn't get that comma work through peer review today either. During this time, along the western edge of North America, an oceanic plate, I think I missed a, did I miss a paragraph there? Okay, this view of the origin of the canyons held sway through the late 19th and early 20th century and was advocated by the two most prominent Grand Canyon researchers of that era, Clarence E. Dutton and Charles D. Walcott. The only significant dissent came from USGS geologist Samuel Emmons, who argued that the Green River through Lador Canyon was superposed rather than antecedent. Well, nowadays we know that the main period of buckling and uplift of rock strata in the western interior occurred at about the same time the dinosaurs became extinct, and we call this event the Laramide orogeny. Just prior to Laramide time, at about 80 million years ago, the region that's now the lofty Rocky Mountains and Colorado Plateau lay near sea level, as it had for at least the previous 500 million years. So the Laramide was quite a change. During this time, along the western edge of North America, an oceanic plate plunged beneath the edge of the continent, a process called subduction. In so doing, the downgoing plate loses the water trapped in the sediments of the ocean basin, which gets dragged down. If I can get this movie to move, there we go. The water gets dragged down into the mantle and causes it to melt. In modern subduction zones, there goes my volcanic flow there, you like that? The overriding plate usually hosts chains of active volcanoes called arcs. So that string of volcanoes, we'll just use the word arc for shorthand. On continents, active arcs are usually typified by huge stratovolcanoes. Subduction also causes deformation of the crust in the overriding continental plate, forming faults and folds like we see in the Laramide. So this map shows the tectonic situation in the western U.S. about 80 million years ago, just prior to the Laramide orogeny. The area close to the coast, including modern California, hosted a long chain of volcanoes, the roots of which make up the modern Sierra Nevada landscape. Deep modern valleys like Yosemite and Kings Canyon are carved into the granites that make up the core of this ancient arc, shown by the red patterning here on the diagram. The continental interior was an undeformed, flat-lying plain near sea level, accumulating sediment eroding off the arc. So it was basically as flat as Kansas, or even flatter, at that time. Now, watch what happens to the interior. We go to 55 million years ago. After 80 million years ago, the interior, including all of the Rocky Mountain states, was compressed and folded like a giant wrinkled rug, in some places very gently, like the Grand Canyon area, and in others more dramatically, as in the Rocky Mountains. The vast lowland plains rose up above sea level, forming upthrust mountain ranges, between which deep basins filled with sediment shed off the uplifts, shown as the dark gray patches on the right side of the map. In northern Arizona, a much smaller uplift in the Grand Canyon region, developed known as the Kaibab Arch. This whole process was completed by about 40 million years ago. For any geologist to gaze into Grand Canyon is to note a long record of slow subsidence of the Earth's crust, accumulating sediment that contains organisms similar to those living today in the shallow oceans. A deep canyon cut almost anywhere in the interior of the conterminous U.S. would have a similar history. The Paleozoic sediments of Grand Canyon proper are only part of the story of subsidence before the Laramide orogeny. As one moves from south to north, or from left to right on this cross-section, younger strata become exposed. First, the rocks of the Vermilion Cliffs at about 240 million years old, then the cliffs of Zion Canyon at about 200 million, all the way up to the Straight Cliffs and Pink Cliffs of southern Utah, where the strata are less than 100 million years old. During the accumulation of most of this sediment, which is about 14,000 feet thick total, the Earth's surface did not deform because the layers were all deposited parallel to one another, as you can see in this diagram. Then laramide buckling eventually led to the erosion of the upper 10,000 feet of these sediments off of the top of the Grand Canyon region, or the Kaibab Arch. Powell and his followers knew about the laramide structures, but had no clue about their precise age. The publication announcing the discovery of T. rex in the Rocky Mountains did not appear until 1905, 3 years after Powell's death. Powell and his followers speculated that the river was born at some time in the early Cenozoic era, or about 50 to 60 million years ago, but had little proof for the age assignment. If Powell was right and the Colorado River is antecedent, then based on modern understanding, it would have cut Grand Canyon in the late Mesozoic while the dinosaurs were still around. Yet nowadays, most geologists regard Grand Canyon as being less than 6 million years old. So what did geologists discover over the last century that left Powell's inevitable conclusion of antecedents languishing in the dustbin of history? The answer lies in what students of the Grand Canyon refer to as the Muddy Creek problem. In 1934, Stanford geology professor Elliot Blackwelder inaugurated a new era of research in a paper concluding that the Colorado was a geologically young river. He noted that regardless of what one infers about the river upstream of Grand Canyon, its reach between Grand Canyon and the Gulf of California is cut into the bottoms of a series of basin and range valleys containing late Cenozoic sediments, visible here in the lower part of this Google Earth image, right there at the finger, labeled as basin fill dissected by the Colorado. These valleys and the ranges that surround them were formed not by compressive rumpling of the rug, as in the laramide, but by stretching of the Earth's crust. The main phase of this process began about 20 million years ago to create the Basin and Range province. The ranges are formed by faulting of the Earth's crust, cutting it up into a series of blocks, analogous to a row of giant dominoes. As the crust stretches apart, the blocks topple over, with mountain ranges formed along the up-tilted parts of the basin and up-tilted parts and basins over the down-tilted parts of each block. After tilting, these basins gradually fill up with flat-lying sediment. Blackwelder and later geologists studying these deposits demonstrated that they were all composed of gravels derived from the immediately surrounding ranges. In stark contrast, the gravels carried by the modern Colorado River contain abundant exotic rock types, pebbles and cobbles, that can be traced to sources in the Rocky Mountains and on the Colorado Plateau. They reasoned that the Colorado could not have been present until after the deposition of these very young sediments, or else they too should contain the exotic gravel. The transition between the Colorado Plateau and the Basin and Range is razor sharp where the Colorado exits the plateau, in what is now the Lake Mead area, where Powell's expeditions terminated at the Grand Wash Cliffs. About 12 miles northwest of the new Grand Canyon Skywalk, which we'll see in a bit, is the nemesis of anyone with even the mildest case of acrophobia. You don't even want to think about it. The first major valley west of the plateau is called Grand Wash Trough, where a sedimentary unit called the Muddy Creek Formation was deposited between 13 and 6 million years ago, on top of steeply tilted fault blocks containing the same Paleozoic strata as found in Grand Canyon. This is well observed in the vicinity of Wheeler Ridge, which sits down there in the middle of Grand Wash on the left side of the diagram, and near a place I'll get to in a minute called Sandy Point. Here we're looking north up Grand Wash Trough. You can see the tilted strata in the domino fault block comprising Wheeler Ridge on the left. The dissected basin-filling sediments of the Muddy Creek Formation in Grand Wash Trough are exposed around the lake and in the near foreground. Farther to the right are the Grand Wash Cliffs, which form the western margin of the Colorado Plateau, and the point where the Colorado exits Grand Canyon is on the far right. As noted by all geologists who've studied them, beginning with Yale geologist Chester Longwell in the 1930s, gravels in the Muddy Creek were all derived from either the Grand Wash Cliffs area or ranges immediately to the west of the Trough. They definitely don't contain exotic detritus and are in fact not even river deposits. This east-west section with the plateau to the right and Grand Wash Trough to the left shows the Muddy Creek in orange sitting on tilted fault blocks. As is apparent from the section, after tilting and basin filling, the area was erosionally dissected by the Colorado by more than 1,500 feet, exposing in three-dimensional detail the basin fill. After dissection, the gravels that do have the exotic composition of the modern river gravels were deposited on the dissected Muddy Creek throughout the Lake Mead region, most importantly at Sandy Point, shown here on the left side of the section. Here, these post-Muddy Creek river gravels, colored white, are overlain by a lava flow forming the Black Cliff that was dated by the USGS at 4.4 million years ago. This sets the timing of dissection of the Muddy Creek Formation to have occurred between 6 and 4.4 million years. Now, Sandy Point isn't the only place where the transition from local gravel to exotic gravel is observed. Near the terminus of the Colorado in the Salt and Trough region, a thick blanket of sediments has been accumulating in deltas and the shallow ocean over the last 7 million years, including the Imperial Formation, located in the black areas there in the lower left part of the diagram, and shown in their present position and in a restored position that accounts for shearing along the San Andreas Fault over the last 6 million years. As demonstrated by a recent study led by Rebecca Dorsey of the University of Oregon, the older part of the Salt and Trough sediments contain only locally derived gravel, but at precisely 5.3 million years ago, they also begin to include exotic Rocky Mountain detritus, pinpointing the time at which the Colorado River came into existence in the area. It's almost an exact replay of the situation at Grand Wash Trough. These observations are fortified by our current understanding of how Salt and Trough and the Basin and Range came into existence. As reported in a January 2008 Watson lecture, a Caltech team led by Professor Joanne Stock studied volcanic deposits on either side of the northern Gulf of California. They showed that a single volcanic field with youngest eruptions dated at 6.1 million years are found on either side of the Gulf and are now more than 140 miles apart. Putting the field back together shows that the Gulf of California did not exist 6 million years ago. Here's a movie constructed by Tanya Otwater of UC Santa Barbara showing how the plate tectonics of this whole system works. The movie starts at 38 million years ago, with the black bar on the right showing the time in millions of years ago. You can see initially that there is no gulf and that an ancient tectonic plate called the Farallon plate is converging on the North American plate, a continuation of the subduction that created the Sierran Arc way back in the Mesozoic. I get this thing to move. As the system evolved, the diverging plate boundary, or mid-ocean ridge, between the Farallon and Pacific plates impinges on the edge of the North American plate. After this, the plate boundary gradually changes over from convergence to lateral shearing and extension between Pacific and North America. As the boundary grows, the Pacific plate starts tugging away at North America, causing stretching and the formation of the Basin and Range. Then, at about 6 to 8 million years ago, the plate boundary jumps eastward into the continent, tearing off the Baja Peninsula to open the Gulf, at the same time giving birth to the modern San Andreas Fault system. So, the plate tectonics, the opening of the Gulf, the birth of the San Andreas, and the birth of the Colorado all fit together remarkably well with pinpoint timing. Given this history for the Colorado, what does it mean for the formation of Grand Canyon? If the acrophiles among us stand on the skywalk and ask, when and how did this form, it seems inevitable, to borrow an adjective from Powell, that the vast upland plateau we're standing on was incised by the Colorado River, forming the canyon. This in turn leads to the conclusion, maybe even inevitable, that the canyon was carved by the Colorado River over the last 6 million years. For Blackwelder and mainstream geology up to the present, it's game, set, and match. But as you may have guessed from the title of this evening's presentation, this is not where we're heading. The logic applied by Blackwelder and later workers applies to the river, but doesn't necessarily apply to the canyons through which the rivers flow. The basin and range valleys are obviously young, but what about Grand Canyon and its tributaries, such as Peach Spring Canyon? In the 1960s, Richard Young, now a geology professor at the State University of New York at Geneseo, began studying a succession of ancient river gravels like these deposited in Peach Springs Canyon, which flows northward into western Grand Canyon, near the Skywalk. He and his colleagues have shown that these gravels are no younger than 50 million years old, and that they were deposited in river channels that also flowed northward toward Grand Canyon. This view looking north over western Grand Canyon shows the Peach Spring Canyon drainage and where it flows into the Colorado. The next slide is a close-up of the area outlined in the white box in the center, where some typical exposures of Young's gravels are found quite close to Grand Canyon itself. These gravels, which include the two dark-colored patches shown with the arrows, tell us a lot about the topographic history of the area and the time of canyon cutting. They basically fossilize, if you will, the topographic surface 50 million years ago and tell us that it was not far above the modern river channel. Now, because the old Paleozoic strata in the surrounding uplands and on which they're deposited were still there 50 million years ago, they tell us that the ancient tributary canyon was about as deep then as it is today. If a similar gravel were found in the bottom of Grand Canyon, then Grand Canyon would have to have formed prior to that time. Unfortunately, the oldest river gravels in Grand Canyon are a measly 700,000 years old. This map shows the distribution of canyons defined by the ancient river gravels, with the big, bold arrows, which come to within 5 miles of the Colorado River and have a geometry that's fairly similar to the modern drainage. Let's look at a cross-sectional profile where that big line is drawn through the largest of these channels that runs from the town of Truxton, Arizona, to the south, almost all the way to Grand Canyon. Here you can see the Paleozoic layers are shown in white, gray, and blue, and the position of the ancient river gravels is shown in orange, whose elevations come to within 2,000 feet of the bottom of western Grand Canyon, just 5 miles away. Along the southern reach of these canyons, to the left near Truxton, the local relief between the canyon bottoms and surrounding topography of the Hualapai Plateau is about 4,000 feet, nearly as deep as modern Grand Canyon. On the right side of the profile, you can see that the north rim of Grand Canyon is about 3,000 feet higher than the northernmost ancient gravels, and so there is an element here of what we might call a river Styx paradox. Namely, that unless some form of fairly deep canyon already existed 50 million years ago in Grand Canyon, the ancient river system has no outlet except for the grottos of Lucifer, let's call them. This fact has bedeviled young canyon enthusiasts for decades. If Grand Canyon is so young, what are these old canyons doing right here next to it? And how did they escape from Grand Canyon? Young himself has long hypothesized that the ancient rivers continued northward along a precursor to Grand Canyon and into the Bryce Canyon area of southern Utah, shown as the projected hypothesis 1 on this diagram. But it's also possible, if one allows for a minute, that Grand Canyon is also ancient, that the river flowed down modern Peach Spring Canyon into a canyon of nearly the present depth of the Grand Canyon, as shown as hypothesis 2 with the steeply plunging dashed line into the bottom of Grand Canyon. The gravels in Peach Springs Canyon leave us wondering about Grand Canyon because there aren't any old gravel deposits that we know of at the bottom or anywhere on its walls. But thanks to Ken Farley and his colleagues in the Noble Gas Laboratory here at Caltech, there's another way to get at this information, which is through the ancient temperatures of rocks within and around the canyon. It's well known that if we drill a hole into the earth, the temperature increases at a rate of about 40 degrees C for each mile that we drill down. As shown in this diagram, published last September in Physics Today by 2 former members of Ken's research team, Peter Reiners and David Schuster, the temperature increases downward in the upper mile or 2 of the crust at about the same rate whether you're standing on a mountain or down in a valley. As shown in this diagram, this effect dies out downward, but all at the depths we're interested in, say the last 1 to 2 miles of erosion of Grand Canyon, the thermal imprint of erosion, or the palimpsest of erosion, is quite strong. The key to unlocking the timing of a rock's cooling comes from radioactive decay of uranium and thorium, which decay to lead and in the process emit 8 alpha particles, which quickly add 2 electrons and become helium atoms. By measuring the ratio of uranium and thorium to helium, we are measuring the time at which a mineral in a rock begins accumulating helium generated by decay. This method of dating the time of formation of uranium-bearing crystals in rocks was among the first attempted many, many decades ago, but it was immediately discovered that because helium atoms are so small and they contain no charge, they easily rattle their way out of crystals at temperatures down in the earth. Calcium phosphate, the mineral apatite, is a common mineral in most rocks that also contains uranium and thorium. What turns out to be a bust for measuring the age at which crystals form, however, is a boon for measuring the time at which the mineral was last at a certain temperature, because the rate at which helium escapes depends mostly on the temperature of the crystal while erosion is going on above it. Through careful experiments conducted by Ken and his team over the last 15 years, they've determined that all the helium leaks out of apatite at temperatures above 70 degrees C, some of it leaks out between 70 and 30 degrees C, and very little leaks out below 30 degrees C, at least at geological timescales. 30 degrees C is only 5 degrees warmer than the surface temperature at the bottom of Grand Canyon today, so if a sample quickly cools from 70 to 30 due to erosion, the helium age will give the time at which erosion had brought the sample within a few hundred feet of the surface. In fact, the age for such a sample in a river gorge would represent a sort of virtual gravel deposit, because the river gravels of that age could not have been very far above the sample. So you don't really need the stinking gravels. With this concept in mind, in 2005, Ken and I convinced postdoc Rebecca Flowers to collect and measure helium ages in apatite crystals in the Grand Canyon and environs. Upon completion of her measurements in Ken's lab, she came into my office and announced that in eastern Grand Canyon, the temperature history of samples on the canyon rim were identical to those in the bottom of the canyon, all the way back to the early Cenozoic. The basic idea is shown here. Prior to carving a canyon, shown on the left, sample A, at the bottom of what will become the canyon, was about 40 degrees C hotter than the same sample B on the plateau. But after 70 million years ago, as shown in the middle, the samples are at the same temperature, indicating that the canyon was in existence by then, with each sample at the same depth below the surface, about a mile down. Then, at around 20 million years ago, shown on the right, an additional mile of erosion occurred, bringing both canyon and plateau samples fairly close to the modern surface. This history completely flies in the face of the widely accepted young canyon hypothesis. So going in, we expected to find that the bottom of the canyon was a mile deeper and therefore 40 degrees C hotter than the rim up until 6 million years ago. Well, for better or worse, it wasn't. The situation in Western Grand Canyon is even more dramatic. Here, samples from the bottom of Western Grand Canyon were collected in the same area where the Peach Spring drainage empties into Grand Canyon. The helium ages were even older than the Eastern Grand Canyon samples and showed a single pulse of cooling down to about 30 degrees C 70 to 80 million years ago. Previous work using a system called fission track dating showed that these samples were above 100 degrees C just prior to that time. So the combination of the two indicates that the bottom of the gorge has been within about 1,000 feet of the surface since a time when T-Rex was still thriving. This was the virtual gravel deposit we were looking for. It makes the river Styx paradox for the Peach Spring gravels much worse because it requires the ancient canyons to have drained nearly all the way down to the bottom of modern Grand Canyon, per hypothesis 2 mentioned above, leaving them with a 4,000-foot climb to get out over the North Rim. The ancient Peach Spring canyons have nowhere left to go but through a nearly fully formed Grand Canyon. Thus, T-Rex's view of Western Grand Canyon, assuming he was able to have a look, was not terribly different than the acrophiliacs enjoying the view here. The next question was, if Grand Canyon was already sitting there before the Laramide, it was presumably carved by a huge antecedent stream, knifing its way downward as the plateau rose during Laramide deformation. But remember that before the Laramide, California was the site of a chain of arc volcanoes, and Utah was sitting at sea level, slowly subsiding and collecting sediment. To the question, which way did the river flow through this canyon, the most logical inference is that it was draining from the mountainous arc in California toward sea level in Utah, not the other way around. It would have looked pretty close to something like this, with uplifted regions on the coast indicated with the red lines, draining northeastward onto a coastal plain, with the rivers shown in blue. This inference is confirmed, if not made inevitable, by the character of rocks in southern Utah deposited between 80 and 70 million years ago. In recently published papers, a team from Idaho State University, led by Paul Link, as well as earlier data, showed that the flow directions of river currents in southern Utah were northeastward at that time, the flow data shown as the black arrows near the top of the diagram. Their work also showed that the sands themselves, like most sands, contain trace amounts of a mineral called zircon, which, unlike most other sand grains, contains uranium. The decay of uranium to lead in a zircon crystal dates the time of formation of the crystal. In contrast to the alpha particles, the final decay product of lead is highly bound in place and does not leak out. A large fraction of the zircon grains in the Utah sandstones crystallized between 70 and 80 million years ago. The only possible source for these zircon grains, which crystallized during the cooling of magma, is the active arc on the coast. So putting it all together, a major river system originating in California was flowing through Grand Canyon before, during, and after it formed, delivering detritus from the mountainous arc northeastward into the basins of southern Utah. Given the convention of naming a river after its source region, I refer to it as the ancient California River, which, according to the cooling history data, carved Grand Canyon in the age of T-Rex. It flowed in the opposite direction of the modern Colorado, which was born only 6 million years ago, and of course functions to carry detritus from the Rocky Mountains into the Gulf of California. This picture of how Grand Canyon formed is a lot closer to Powell's than it is to the Young Canyon hypothesis, differing from his basic ideas only in having the river flow to the northeast during carving of Grand Canyon rather than to the southwest. Now the question becomes, what the heck happened to the canyon in between 70 and 6 million years ago? The answer to this is pretty clear, again relying on source regions of the basins upstream and downstream of Grand Canyon. There are not only thick deposits of this age in southern Utah, but there are counterparts right here in Southern California that have been very carefully studied over many years. The most famous of these is the Sespe Formation, whose rocky crags make it the prime geological formation in Southern California to stage shootouts in movie and TV westerns. Almost every rock outcrop you see in an episode of Gunsmoke is Sespe. When we account for shearing on the San Andreas Fault over the past 6 million years, all of these deposits restore back to a position about where the modern Colorado River empties into the Gulf of California, shown in the beige shaded area marked LA in the middle. Between 60 and 50 million years ago, a remarkable transition in the sources of sand and gravel occurs in both the Southern California and Southern Utah basins. In Utah, strata younger than 60 million years start losing their young arc zircons and become more like the modern Colorado, deriving their sand and gravel from the northern and western sources. Our deposits here in Southern California, like the Sespe, deposited between 70 and 60 million years ago, are made up of sand and gravel derived only from the arc, but beginning about 55 million years ago, start picking up material derived well into the northeast of the arc, perhaps as far northeast as Grand Canyon, as shown here, with WG showing the position of western Grand Canyon and the letters EG showing the eastern. About 20 to 30% of the rock fragments contained in these gravels are a rock type called orthoquartzite, which is a sandstone tightly cemented with quartz that is extremely resistant to breakage when being transported in river channels. Detailed studies by Jeffrey Howard, now of Wayne State University, show that these orthoquartzites are derived from eastern California and Arizona, transported to the coast by what he refers to as the Gila and Amargosa Paleo rivers. The data thus collectively show an expansion of the drainage area along the coast into the continental interior. At exactly the same time, a contraction of the interior drainages occurs away from the arc and into the Rocky Mountains. Since this drainage has headwaters in Arizona, it makes sense to refer to it as the Arizona River. So let's sum it all up with a series of geological sections at the locations shown on this map, highlighted in yellow, with coastal California on the left of the diagram and interior Utah on the right, and then I'll be glad to field some questions from the audience. First, the antecedent California River drains from the mountainous coastal arc to the interior basins of southern Utah, which lay near sea level, facing a large, shallow interior ocean that stretched as far east as the Gulf of Mexico, just prior to the Laramide orogeny. In brown are ancient Precambrian basement rocks that form the crust of the southwestern U.S. In blue are Paleozoic sediments that now form the walls of Grand Canyon. And in green are the Mesozoic sediments deposited above them. And in pink are granites of the arc. By 70 million years ago, in the lower frame, the interior had risen to an elevation of at least 5,000 feet, and the California River had carved Grand Canyon. At this time, the drainage divide was still along the center of the arc, shedding thick deposits southwestward into the basins around LA. Now let's fast forward to the situation near 55 million years ago, after T-Rex has long since vanished from the scene. At this time, uplift have migrated even farther into the continent, into the southern Utah basins. The drainage divide is now well into the interior, trapping the southern Utah basins and changing their sediment source to the newly formed Rocky Mountains. The shift of the drainage divide reversed the course of the river in Grand Canyon from northeast to southwest, now sending its detritus out to the coast, including that of the ancient Peach Springs gravels, which have composition very similar to the Sespe, but not similar to the southern Utah deposits of the same age. The consistency of sediment sources for the next 30 to 40 million years and the consistency of temperatures of rocks that make up Grand Canyon both support this idea. An important climatic transition occurred in this middle period, reflected in the deposition of extensive sand seas across the Colorado Plateau, as recently documented by a research team led by Steve Cather of the New Mexico Bureau of Mines. The streams were likely quite dry at this time, as indicated here by the decreasing number of arrows that are shown along the river grades over this interval. Now, by 15 million years ago, shown in the lower frame, the downstream reaches of the Arizona drainage were disrupted by the tectonic stretching of the Basin and Range Province, forming deep basins that drained internally, such as Grand Wash Trough and other basins downstream. This basically wiped out the Arizona River. At this time, the supply of interior detritus to the coast was cut off. Just prior to this time, the erosion level of eastern Grand Canyon had lowered another mile, reaching a position very close to the modern one, about 10 million years before the Colorado River had come into existence. After this time, only locally derived detritus filled the extensional basins as originally observed by Blackwelder, Longwell, and geologists up to the present day. This resolves the Muddy Creek problem because it does not require Rocky Mountain detritus to have moved through Grand Canyon prior to 6 million years ago. Indeed, it only requires the feeble headwaters of the former Arizona River to lay upstream of Grand Wash Trough at a time when the climate became too arid to have supported significant river flow through Grand Canyon. The end of the story comes with the birth of the Colorado. By about 6 million years ago, the climate began to become less arid, and the Earth began to move toward our current relatively cold and wet state at this latitude. The event is also recorded by the presence of enough water to create a number of large temporary lakes in the southwest. The maximum extent of each of these lakes is shown in this diagram by the yellow shading. Deposits associated with the highest of these lakes, called the Beta Hochi Formation, blanket much of northeastern Arizona on the right. According to a theory now favored by some but not all geologists, the birth of the Colorado occurred when a cascade of lake spillover events propagated downstream from Lake Beta Hochi. The first spillover quickly ran down an already existent Grand Canyon and quickly filled a Lake Hualapai, occupying Grand Wash Trough and environs, which then spilled over into various other lakes downstream. Each spillover event would have drained the upstream lake, immediately dissecting it by erosion, as in the dissection of the Muddy Creek Formation by 4.4 million years ago, when the Rocky Mountain gravels had arrived at Sandy Point. The upper frame here shows the system just prior to Lake Beta Hochi overtopping and spilling into Grand Canyon, which likely increased the hydrologic discharge through the canyon by 2 orders of magnitude or more, giving its new and very wet Rocky Mountain headwaters. This event finally destroyed the drainage divide between the interior drainages of the Rocky Mountains and the Basin and Range, creating a river with headwaters in Colorado that momentarily, by geological standards, filled Lake Hualapai. The remaining spillover events would have easily breached the local divides between the basin and range valleys until the lowest of the lakes finally spilled over into the newly formed Gulf of California at 5.3 million years ago. This event not only reintegrated the Arizona River, but connected Rocky Mountain sources with the Gulf, and so deserves the name Colorado River, not Arizona River. By now, Grand Canyon is a very old canyon, and in this last phase of evolution, it was 70 million years old and serving as a conduit, serving whatever function its surroundings dictated. Grand Canyon was thus in no sense carved by the Colorado River, which is of little consequence to its origin. And now I'd love to hear some of your questions.
This program is brought to you by Caltech. Visit us at caltech.edu.